ELEC2 2019 question 9. Okay, so for part A, digital data is transmitted to the head office of a bank from one of its branches via an optical fiber link. Amplifiers X and Y are used to boost the signal amplitude. So you've got a diagram with an input, we've got an amp X, we've got 25 kilometers of optical fiber, we've got amp Y, and then we should have an output, although the diagram says input. Amplifier X and Y both have a gain of plus 30 decibels. The optical fiber link has an attenuation of 2 decibels per kilometer and is 25 kilometers long. At the transmitter, the input power is 2.5 milliwatts. Calculate, for number 1, the overall gain of the system in decibels. Well, this system has gain from both of the amplifiers, but it's got losses because of the optical fiber. So the gain from the amplifiers, and because there's 2 of them, is going to be 2 times 30. But it's going to lose 2 decibels for each of the 25 kilometers that there are for the optical fiber. So we've got to do 2 times 25 for the losses. And this means that overall we have 10 decibels of overall gain. Okay, for part 2, the output power in milliwatts. Well, we need to look at the data sheet and look for an equation which links gain and power, and hopefully you're aware it's going to have a log in it because we're dealing with the power of items in decibels. So the equation we're looking for is gain equals 10 log to the base 10 of power out divided by power in. Now we can't use the equation in this format, and you've either got to have the ability to rearrange it, or you're just going to have to remember the rearranged form, because the rearranged form that we need as far as this is concerned is power out equals power in times 10 to the power of the gain divided by 10. Okay, so the values for this are 0.0025 for the 2.5 milliwatts, and it's going to be 10 to the power of, and it's going to be 10 over 10. Now hopefully you're aware that 10 over 10 is 1, 10 to the power of 1 is 10, so this is 0.0025 times 10, which gives us an answer of 25 milliwatts, or 0.025 watts. Okay, I'll just try and make that look more like a 2. Right, so for B part 1, the diagram shows the typical structure of an optical fiber cable. Identify the components labelled X and Y. Well, you need to know those 4 components. It is in the ebook, and the center of an optical fiber is called the core. Then the medium around the core is called the cladding. Then you've got another layer around the cladding called the coating, and around the coating is the jacket. Sometimes there is a 5th layer between the coating and the jacket, which is a strength member. It's like a coating, normally with wire in it, which gives the optical fiber some strength. So as far as X and Y is concerned, it's core and it's cladding. Okay, for part 2. The signal travels from amplifier X to amplifier Y using total internal reflection. Describe 2 conditions necessary for this to occur in the fiber. But if you think back to GCSE physics, hopefully most of you can remember that total internal reflection only occurs when you go from a dense to a less dense medium. in physics terms, we don't talk about density, we talk about light, and we talk about refraction or total internal reflection. We talk about refractive index. So refractive index is going to be one of the things that we need to describe. And then the other is the conditions around the type of angle that this works at. So in terms of an answer, it should be that the refractive index of y is less than the refractive index of x. All right, so we've got it going from a dense to a less dense medium. And the next one is that the angle of incidence must be greater than the critical angle at the boundary xy. So, C part 1. The signal received at the output is converted back to an electrical signal, which is then regenerated by a Schmitt trigger subsystem. The following graph shows the characteristic for this Schmitt trigger. Design a Schmitt trigger circuit based on a single op-amp that has these characteristics. Draw the circuit diagram for your design. Well, before we can draw any circuit diagram, we've got to be able to interpret the graph. And there are three things that we should be able to take away from the graph. And they are that it saturates at plus or minus 10 volts, and that's the horizontal maximum values. That it switches at plus or minus 8 volts, and they are the vertical lines. And it's symmetrical. I suppose that there is a fourth one we could take away, if we wanted to, that this is a non-inverting Schmitt trigger. All right, and the graph shape shows us that that's a non-inverting Schmitt trigger. Okay, so we need to be able to draw this. So we've got our op-amp, and we're going to put in our plus and our minus values. Hopefully you remember with Schmitt triggers, we're going to have two resistors, one on the right hand side of the connection to the non-inverting input and one on the left hand side. The output is going to be connected to that right hand resistor. The input value, I'm going to call it V in, is on the left hand side of the left resistor, and we've got a reference voltage. Now, what we need to do is put some values to this from the information that we've been able to glean. Well, because it's symmetrical, and it's symmetrical around 0 volts, Vref is going to be 0 volts. We're told, or when we look at the graph, where we can tell that it saturates the output at plus and minus 10 volts. So we know that the output is going to be plus or minus 10 volts. And we know that V in, and these are the values which are vertical in the y-axis, we know that these are plus or minus 8 volts. Now the beauty of this is that we can see from the graph that this value here is also going to be 0 volts, because that's how Schmitt triggers and op-amps work in this type of condition. Now that is key, because what that tells us is between V in and that point, let's call it X. So between V in and X there's plus or minus 8 volts, and between V out and X there is plus or minus 10 volts. Now the beauty as far as this particular circuit is concerned is that if the output is minus 10 volts and we want to switch it to plus 10 volts, well that means that we've got 10 volts between that minus 10 and 0 volts, and in order to switch it to a plus output we need a plus input which means that we're going to have plus 8 volts as V in. So between V in and X there's going to be 8 volts. So we've got a 10 to 8 ratio. So if we just record that for that particular output, so if the values are when Vout is minus 10 volts, then Vin will be plus 8 volts to make it change, which means that the voltage for R1 is 10 volts and the voltage for R2 is 8 volts. And that's if this is R1 and this is R2. Well, that means that essentially R1 over R2 is going to be 10 over 8, which means we can give it some nice easy values, and our values that we're going to give are that R2 is 8k, in fact no, let's make that 80k, and there's a reason for that. Remember, the smallest value you should be using is 10k, and we make R1 100k. Okay, on to the last question. Complete the second graph to show the effect of this Schmidt trigger on the signal given in the first graph. So we've got this test signal, the first graph, which is like a sawtooth and shown here. And what we need to do is draw the resulting output. Now I'm going to do it on the same graph, but reality is you'd need to do this on a separate graph on the paper. Now, again, as we were saying earlier, there are some conditions that you should need to be aware of so that we know exactly how this works. And things that I need to remember as far as drawing this graph is concerned is that it's a non-inverting Schmidt trigger, right? That means that you need to go to the upper value in terms of switching in order to switch it from your lower value to your higher value for the output, and vice versa. You go to your lower switching value to switch it from your higher to your lower output value. And we know that when Vin is bigger than 8 volts, Vout goes from minus 10 to plus 10 volts. And when Vin is less than 8 volts, Vout goes from plus 10 volts to minus 10 volts. And that's because of the non-inverting nature. And we've got to get those 10 volts the right way around, minus 10 to plus 10 or vice versa. So what does this mean? Well, it means that on the very left-hand side of this graph, we must be starting with a lower value. And only when it gets to 8 volts, plus 8 volts, does it switch to the higher value. Well, the lower value is minus 10. So we know it's going to start at minus 10. And it's only when it gets to plus 8 volts, which is up here, that it goes to plus 10. So we know that we're going to get a change there. Now, because of the Schmidt trigger nature of this, it's got to go back down below minus 8 volts in order for it to switch from plus 10 volts to minus 10 volts. So that is going to occur here, and so it's not going to change until we get to this point here. And then with this graph, it's going to change one further time when the graph goes back up to above plus 8, and it's going to just change here. So you're just going to get a change just before it disappears off of the page. And so I'm just going to redraw my blue line in, and so it's going to be about here. Right, so now we can draw the output graph. So it's going to go straight along, and then it's going to switch when it gets to plus 8 volts on the sawtooth. It's going to then stay at plus 10. And then it's going to go to minus 10 when the sawtooth goes to minus 8. And then it's going to stay at minus 10 just until we get just before it disappears off the graph. And that concludes question 9 and component 2 for 2019.